Electromagnetism refers to the creation of a magnetic field for the movement of electrical charges. When electrically charged particles move, they create an electric field. Likewise, when electrical current moves through a wire, a magnetic field is created around the wire. Electromagnetism is one of the most important forces in our daily lives. It is hard to go through a day without using devices which utilize electromagnets. Electromagnets can be found in devices such as loudspeakers, electronic door locks, doorbells, and even fire alarms. Today, we will be constructing an electromagnetic motor model, more specifically, a DC motor, which will demonstrate several fundamental concepts of electromagnetism. So how does a DC motor work? In our circuit, when electric current passes through the paper clips to the copper coil, a magnetic field is created around the copper coil, turning it into a temporary electromagnet. It is this temporary electromagnet which drives the motion of our motor. In addition, looping the wire also increases the strength of the magnetic field around it, which is why we have coiled the copper wire multiple times to increase the strength of the magnetic field around it and to turn it into a stronger electromagnet, thus making the motion of our motor stronger as well.
With the basic idea of electromagnetism established, the first concept we'd like to cover brings up a question. What does DC in a DC motor actually stand for? Well, DC stands for direct current. In a direct current circuit, current moves steadily in only one direction, as the magnetic field near the wire causes electrons to flow in a single direction along the wire. Thus, when DC electricity is passed through a wire, the magnetic field created causes electrons to flow along the wire in only one direction. When current from the battery passes through the wire coil, it creates a magnetic field around the coil, turning it into a temporary electromagnet. The poles of the disc magnets then repel the like poles of the electromagnet, causing the wire coil to rotate half a turn. Following half a turn, the part of the wire which is coated with ink and has thus been insulated comes into contact with the paper clips. This leads to a break in the circuit, stopping the flow of current. The wire coil continues turning due to gravity until the uninsulated part of the wire end comes into contact with the paper clips again. This closes the circuit and allows current to flow again, thus repeating the process and causing the wire coil to spin continuously. This brings up another fundamental electromagnetic concept, Fleming's left-hand rule. What is Fleming's left-hand rule? Well, basically, when a wire carrying electric current is moved in a magnetic field of a magnet, the magnetic field of the magnet exerts an attractive or repulsive force on the magnetic field induced around the wire coil, causing the wire coil to move. The direction of the wire coil's motion is perpendicular to the direction of its magnetic field. This is called Fleming's left-hand rule. As can be seen in this diagram illustrating Fleming's left-hand rule, the index finger points the direction of a magnetic field, and the middle finger, at a 90-degree angle to the index finger, points the direction of the electrical current. This then means that the extended thumb forming an L with the index finger points the direction of the force exerted upon the particle. This understanding of Fleming's left-hand rule would tie back to the idea of direct current, which we have established earlier, and explains the rotation of the coil in the DC motor. As the flow of direct current is unidirectional, this causes the magnetic field around the wire coil to only rotate in one direction as well, explaining why the wire coil only rotates in a specific direction, which according to Fleming's left-hand rule is perpendicular to the direction of its magnetic field. The direction of motion, i.e. the coil rotating, is also perpendicular to the current being supplied into this circuit.
Here is how we constructed our DC motor. First, you will need these materials: insulated wire, one D-cell battery, a permanent marker, a wire stripper, one large plastic cup, two disc magnets or just two magnets, two large paper clips, and two alligator cables. I'll be teaching you how to construct the model. First, you need to take the coil, the wire, and coil it around a D-cell battery several times. And as you coil, you should try to leave about 6 centimeters of free wire at each end. Here is a sample coil that we have done earlier, like so. As you can see, there's about 6 cm of free wire at each end. Now, strip the plastic insulating coating off the ends of the free ends of the wire. As you can see, we have taken off the plastic insulating coating of the free ends of the wire, shown here and shown here. And try to straighten it as well. See? Yes, you should try to be as straight as possible. Next, putting the coil against a wall or facing you like this. Take a permanent marker and color the top half of the wire like this. This is a very important step, as this will cause a break in the magnetic field and will cause it to continue spinning. Next, invert the large plastic cup and put one of the disc magnets on top of the cup and the other one on the inner surface of the cup. This will hold both in place as they are attracted to one another. Next, for the two large paper clips, you should try to straighten the outer ends to form a P. We have two over here.